So integrals have a limit definition, much like derivatives. If you remember the derivative definition with the limit. Okay, integrals are based on limits too. The definite integral is, right? So if I were to ask you, well, what is the integral from 0 to 3 of x third, right? That's an exact answer, correct? Versus find the left Riemann sum with 3 subintervals of f of x equal to x cubed on the interval 0 to 3, right? Not an exact answer. In fact, is that an over or under estimate? Why? Right. This is an underestimate because f of x is increasing. Right. Left Riemann sums, if you have an increasing function, you're underestimate, right? Okay. So if I do, let's just sketch that up. Right, that's what x cubed looks like on 0, 3. There's the rest of it. You have your right, there's your left Riemann sum, correct? Okay. Obviously it's an underestimate. So how do we get from here to an exact answer? That's the big question. Okay. We need to fill this space in somehow, right? Right. There are 2 different ways we could do it. Anybody think of how would we mess with these rectangles to fill in those spaces? Let me ask you this question then. What in the world is going on here? How would I get a more exact answer using rectangles? Right here I'm using 3 subintervals. Yeah? How could I get? Okay, you can increase that number of subintervals, right? So I could do L6 is a closer to exact, right? But how can I be more accurate than L6? L7, L20. You see where I'm headed? Yeah. So basically what you're doing is you need the number of subintervals to go to what? Infinity. Gross, right? Okay. So what you're doing is you're actually putting an infinite number of rectangles in here. Quote unquote infinite number of rectangles, right? To create this exact answer. Right? Okay, so that's one way that it's tackled. Use a limit as the number of rectangles goes to infinity. Okay. The other way is dealing with the size of the rectangles. What would the size of these rectangles need to approach to go to get an exact answer? Do they need to get bigger or smaller? If they got bigger, would it be a more exact answer? No.
So 0.
Okay, so we need to approach 0. So if you actually take the size of these rectangles and shrink them to approach 0, you're going to get that same result as the number of subintervals, right? Okay, those are the two ways that integrals can be defined based on Riemann sums. Okay. There's a lot more technical language to it. Okay, if I wrote out, let's just write out, find it here. There's a reason I don't try to memorize this, because this is kind of pointless. Yeah, so we would write this one as the limit as n approaches infinity of L of n. Okay, so that's what we would be doing there, right? The number of subintervals is approaching infinity. This one, some funky mod notation. Computer sciences know what mod is, right? Yeah, let's see. I thought it was, oh, there it is. Yeah. Anyway, it's a limit where okay, this is the size. This is the size of the partition. A partition, or the size of the rectangle, right? So it would be the limit as the partition size goes to 0. That's how we would write it. And then it'd have a bunch of funky stuff out here. And the book writes it like this. That's an F, comma. Okay, I'm not going to worry about telling you what those are like, but it gets kind of messy. Okay. So, a couple ways to think about it. Good? All right, so we can write these as what are called as series. It's called series notation.
Wait, so do you ever have to actually calculate the area of one of the rectangles, or do you just write it out? Like, so you don't ever actually have to calculate the limit
With this?
Yeah.
Yeah, we never calculate this anymore because it is such a kind of a pain.
So,
The first year I taught calc, I showed my students how to do this. Not good.
Bad idea?
Bad idea. Very bad idea. So we do avoid it because we have other integration techniques. Much like the definition of a derivative, I show you how to use it, and then we just kind of move on, right? But it is important from a theoretical perspective that we kind of understand the structure behind that. Okay. So, don't be a mathematician. Honestly, it's okay. Series notation. Is a way to write a sum easily and quickly, okay? And it's very straightforward. We'll dive into it a lot second semester, but this is the Greek letter sigma. Okay, it's a capital. Okay. If you're curious about lowercase sigma, I think it's that, if I remember right, but we don't have to worry about it yet. So this would tell me, this says sum up the terms. Okay, that's what that means. And I'm going to go from that's what it's going to look like. All right. So j equals 1 to 4, that just means this is our start. and this is our end, and this is the operator. Okay, so that would be plug 1 in. So we have 1 plus, and then what's next? 2 plus, plug 3 in, and then you end with 4. It's just a sum. Okay. So 3, 6, 10, right? The thing about this is we can change any one of these at any time, right? So I could make that a 0 and I could make that 20, and you would have 21 terms here, right? And you just have 21. Okay. If I wrote that as a Riemann, or as a in series notation, okay, what's my starting value? 0, because it's a left sum, correct? And where am I going to end?
3.
2. Because there's only 3 subintervals, 0, 1, and 2, right? That's where a lot of people get mixed up. So 0, 1, and 2 on x cubed, right? So plug 0 in, plug 1 in, plug 2 in, you got your answer. Right, so this would be 0 cubed plus 1 cubed plus 2 cubed. Right. That's your Riemann sum equivalent. Okay. So like I said, pretty basic notational. Just new, you just have to know how to operate those, right? What we do in second semester is we do this. And this can be any letter. You could put it as n. J and n are pretty common. We make that infinity. Okay. And then we do things like this. Does that, as an infinite series, actually add up to some number? Or does it just keep going on to infinity and it's called diverging? Does it diverge? Okay. Or does it converge? See, these all converge, right? Because they have an actual sum. The question is, does that diverge or converge? Okay. This, in fact, is called the harmonic series and it diverges. Okay. But if I wrote this, that converges. You add up numbers infinitely, but it never crosses some certain number. It converges to that number. Okay, so little differences, that's what we're studying next semester for the most part. That's about a month's worth of work. Gross. Oh, that's funny, gross. Okay, so, but for now, you can just handle these non-infinite series. That's all I'm asking you to do. That's today's like big thing, be able to handle series.
We're just trying to write communication.
Yeah, so half of the homework is being able to compute those.
No, is spiraling.
You've got some Riemann sums and some of these to do, and I don't know what spiraling there is, to be honest. Yeah, there is some. Obviously, you know me better than that. I know myself better than that, so.
You don't have to use spiraling. There's plenty I can use today.
Would you actually, there's plenty of, okay, say that again?
You don't have to put spiraling on. There's plenty of other things I can do today.
There is, but there are plenty of other things you can do. But what would be more valuable in the future than calculus BC? Right?
Well, we just started medical math yesterday in my college course.
A lot of it is. Yeah, I tell you, my wife went through Calc 3 in college. Not necessary.
They were showing us stuff, and I'm like, wow, I don't even need enough calculus.
But they do use calculus. It's just very specific. Like if they're looking for, let's say they are looking for a blockage in the heart with a dye injection, a radiography test. So they'll inject dye, it'll travel to the heart, and then it'll travel out. They're continuously taking pictures of that, either, I don't know, CAT scans or whatever they use. But they're measuring the rate at which the dye comes out of the heart as opposed to the rate at which it's going in, right? And you can figure out total amount of dye that's passed through with calculus if you integrate. And if those rates are vastly different, then they're looking at a possible percentage of blockage, things like that. But that's very specific to a radiologist, obviously, but it's one example. But it's one of those things that you're going to plug the numbers into a computer and it's going to spit the information out, you know. And if you don't have a computer, like you think you might have to do it by hand, if you don't have a computer, you don't have the machine to measure that. So it's like no computer, no test anyways, right? So, it's all text driven, but there are some definite advantages to knowing calc. All right, thanks. Hopefully you got plenty of time to get most of that done.